Okay, hello guys. Today's lesson is going to be super fun because we're going to start talking about equations of uniform motion. And this is really where we start to look at the big five. There are five big equations. We used to call them the Jackson Five. I'll talk a little bit more about that because my physics teacher was Mr. Jackson. So he had us memorize these five equations, and we're going to get to the first out of those today at least. So here we go. First of all, a little bit about bike riding. You remember that scene from Napoleon where he gets hit in the face with his stick. Okay, why is everyone at the gym asking me why I'm sitting still on this stationary bike? I'm going downhill, dude. Mind your business. Yeah, maybe I could be going downhill. You've probably seen me slack off at the gym a little bit. All right, anyway, let's get going. First, a quick look back. I know you're so excited to look back a little bit at the previous lesson. And if you remember the previous lesson, we talked about these types of graphs, which are velocity versus time graph. And you remember if it's A versus B, the A always goes on the vertical axis. So here we have velocity in meters per second, and B is going to be on the horizontal axis, which is time in seconds. And here's the story behind this graph. Okay, so suppose that you leave a class at school and you begin walking towards your next class, which is down the hall to the west. You then realize right here, you realize that you left your textbook in the last class on your seat. So you turn around and you run back, you're running faster, back to the class to get your book. So this is a velocity versus time graph that shows that motion. Now, if they give you this information in a velocity time graph, would you be able to make from this information a position time graph? Okay, so position is over here in the vertical axis now. The X just in meters and time in seconds over here. So would we be able to do that? Usually we've been doing it the other way, but now we're going to try and do it backwards. Do you think we're able to do that? I think we've got the information, we've got the knowledge. Let's try it. Let's give it a try. So you notice in this that there are two main stretches, like two velocities. Here we're going 1 meter per second to the right or west, and then we change direction and we go faster, -3 meters per second. That's the second velocity. So we have to keep into account those two stages when we write this. Now the first stage lasted 15 seconds. So we're going to go from 0 to 15. And the first stage was, I'm just going to write it down here so we remember, +1 meter per second. And it took 15 seconds. So if in 15 seconds we were going 1 meter per second, we must have gone 15 meters in that first 15 seconds because it's a constant velocity. So we went from 0 to 15, there we go, in the first 15 seconds. Now, you'll notice on the way back though, and we went all the way back to 0 because we had to go back to class, to the origin, right? But it doesn't show you that here. What it shows you is in 5 seconds now, 5 seconds, 15 to 20 seconds, you made that whole distance return trip back. So you were going fast, 3 times as fast, actually. So you were going -3 meters per second. So if we went back to the origin, we know that we have to end up somewhere here on this baseline, back at 0 when we're talking about position. So we have to end up here. How long did it take us to end up there? Well, we went a total of 15 meters in the first 15 seconds. So we have to go 3 times as fast. That means we went 15 meters again, but this time, if we're going -3 meters per second, it took us only 5 seconds. Does that make sense? We know we have to go 15 meters. I'm going to multiply that so it cancels out. We went 3 meters per 1 second. 15 divided by 3 is 5. Meters cancel out. So we're left with 5 seconds on top. So it only took us 5 seconds to go that whole distance. So you can see that the other slope is going to look like that. Kind of like that. Let's see if I can make that better. It only took us 5 seconds to get back to 0 on position. Cool. So this velocity time graph we have turned into this. Sweet. We did it. Let's talk a little bit about uniform motion. If you drive your car on a straight road at a perfect, steady 60 miles per hour, you will cover 60 miles during the first hour, 60 miles during the second hour, 60 miles during the third hour, etc. You get it. In fact, you probably get it really well because of our recent trip to Great Basin, where we went on the never-ending, loneliest road in America for a really long time. So that's an example of what we call uniform motion. If you have it on cruise control, you're going to go 60 miles every hour. There are equal displacements. Displacements are a change in x for every change in time. That means if these time intervals are exactly equal, and I tried to draw them in a way that they're equal, that means these velocity vectors are going to be equal. And that makes sense because velocity is change in x over change in time. If this is constant, if that velocity is constant, then you go the same distance for the same amount of time. Okay, so the qualifier any is important when I say during any time interval. Any is important because let's say during the first hour, you spent the first half an hour going 120 miles per hour, and then you stopped for 30 minutes, for the last 30 minutes. So you did go 60 miles during each hour, but you won't have equal displacements, right? You would have gone the whole distance in only a half an hour and then stop. So you won't have equal displacements during successive 30-minute intervals. So that means that motion is not uniform. So whenever we talk about uniform motion, that means you're on cruise control. Okay, that means any time interval, you're going to be going 60 miles. And that always has a motion diagram that looks like this. And it always has a position time graph that looks like this. When the velocity is uniform, it's always going to be a straight line. That means that for every displacement, like we could choose a displacement like this or like this, then the time interval is always going to be the same as well. I didn't draw those great, but you get the idea. So we have already seen how we can determine the velocity of an object here by using the rise over run. And the rise is the change in x and the run is the change in t. Change in x can also be written as final displacement or final position minus initial position, and change in t can also be written as time final minus time initial. That's what this change in means. So if you just rearrange this equation, this one that comes from the definition of velocity, you can get this. If you solve this for final position, you're going to get an equation that looks like this, and this is the first equation that you have to memorize. X final equals x initial plus the velocity times change in t. Okay, and this equation, this is one of the big five. We are going to memorize it. We're going to have it dripping off our tongues. We're going to know it because this makes it so easy. A lot of times we're asked about final position. You start somewhere, you know the velocity that you're going, you know at the time that you're going that velocity, so where are you going to end up? That's what they tend to ask a lot, and memorizing this equation will make your lives a lot easier. Probably because I will hound you less because I expect you to memorize it. Know it, know it, know it, just know it. This is one of the Jackson 5. So if you're old, you will think the Jackson 5 is this, which is Michael Jackson and his brothers when they were young. But if you were in my physics class, the Jackson 5 would mean something different to you. It would mean the 5 equations of kinematics that Mr. Jackson, our teacher, expected us to memorize, and this is one of them. So congratulations, you've learned the first of the Jackson 5. Here's another important feature of this equation. when we look at this first equation, the velocity is given us information like 20 meters per second. And the way that we interpret that means the object changes its position by 20 meters during every second of motion. So in the first second of its motion, it's going to move 20 meters. And it's going to move another 20 meters during the second. The next second will be another 20 meters, and so on. So you can say that the position is changing at a rate of 20 meters per second. So for example, if your initial position is 10 meters, the next position after 1 second is going to be 30 meters. Make sense? So thinking of velocity like this will help you sort of develop an intuitive understanding of how velocity is going to change the position. Okay, this statement just summarizes what I just said, that the velocity, you don't need to memorize that, so I'm not going to circle it in a thought cloud, but velocity tells us how much an object changes its position each second. So position can be thought of as a rate. Here's another way of thinking about it. If your speedometer is saying that you're going 20 kilometers in the first hour, then that means you're going 20 kilometers every hour. If you start out at 0, after 1 hour, you will end up at 20. After 2 hours, you will end up at 40 kilometers. Easy peasy. Let's talk about proportional relationships, because this is another thing that AP test makers love. They love to test us on proportional relationships. This is an example of a proportional relationship. You don't have to memorize this, but it's just a random equation. So y is equal to c times x. When it's written like this, you could also say that y is proportional to x. And what that means is if y goes up, x goes up. The way I think about it is kind of like a fraction. Like this is over 1, this is over 1. And since these are both on the top part of the fraction, if y goes up, it makes sense that x also goes up. C in this example is just a constant. It's a proportionality constant, and it represents a number. You'll see a lot of constants in our equations, but it doesn't matter. C is just a random number that is not going to affect this proportion. If y goes up, x goes up because they're both on top. If y goes down, x goes down. If y increases by 3, x is also going to increase by 3. It's like multiplying a 3 in there. I'm going to write this equation in a different way just to make this point a little bit stronger. What if y was equal to c over x? This is called something different. This is called inversely proportional or inversely related. They're kind of on opposite sides now. Y, if this were a fraction, it would be y over 1. So y is on the top, x is on the bottom. So in this situation, if y goes up, x goes down. They're opposite. And if y goes down, x goes up, because there's an equal sign here. So they have to equal each other. So it makes sense that if there's an equal sign and they're both on the top, one's going to go up, the other one's going to go up. But if they're on opposite sides, one's going to go up, one's going to go down in a proportional way. Questions like that are called ratio reasoning, and you'll see a lot of those on the AP test. This is your classic old-time example. If a train leaves Cleveland at 2 o'clock, ... right? We always hear about examples like this, but these are actually cool solvable problems. So it'll actually be fun. You'll come to enjoy them. Let's read what it says. A train is moving due west at constant speed. So that's important. A passenger notes that it takes 10 minutes to travel 12 kilometers. I'm going to highlight that because that part seems important. It takes 10 minutes to travel 12 kilometers. How long will it take the train to travel 60 kilometers? We know that it's at constant speed, and we know that constant speed, since it's moving west the whole time, is going to be constant velocity. And we know that velocity, based on this equation, is change in x over change in time. So we can write it like this. 12 kilometers is the change in x. It took 10 minutes to do that. And we can figure out the velocity, at least in kilometers per minute. Now, what's the other information that they asked us? How long will it take the train to travel 60 kilometers? So there are a couple ways you could do this. You could use this information to figure out velocity, and then plug in the velocity that you know, plug in the new distance, and get the new time. Or you can do a simple ratio reasoning and simplify it even more. Here's how you would do that. You pull this information out. Now they want to know how long it's going to take us to go 60 kilometers. And I'm going to put X minutes on the bottom. And then this turns into a simple ratio problem. The reason I can do this is because the velocity here, this is a velocity, change in x over change in time, is the same as the velocity here. The train doesn't change in speed. So now all we have to do is cross multiply. You know how to solve problems like that. Cross multiply. So 60 times 10 is equal to 12x. 600 equals 12x. Divide 600 by 12 and you get 50 minutes. And that's the answer. It will take 50 minutes to travel 60 kilometers. All right. That's it for today. Super easy, right? Hope you enjoyed it. Have a great day. Bye.